Hello, everybody. I'm Qianwen Wang, currently a postdoc at Harvard University. Today, I'm presenting our work, Visual Analysis of Discrimination in Machine Learning. The growing use of automated decision-making in critical applications has raised questions about fairness in machine learning, where the decision that the model makes discriminate towards a certain group of individuals. To avoid potential negative social impacts, discrimination in machine learning needs to be better assessed. But how? Take the college admission as an example. If we use a machine learning model to make decisions for college admission, the fact that male students have high admission rates seems to indicate unfair treatments in the admission decision-making. However, if we regroup those students based on their testing score, it then shows no unequal treatment in any of the subgroups. From this example, we can see that the definition of discrimination can be complex. Which individual should be treated equally is not objective and is related to the domain of the prediction tasks. In the example of college admission, if gender directly influences the admission, we will think the decision is unfair. However, if gender is correlated with admission through attributes such as major and testing scores, we may not treat this as an unfair decision, since the values of major and testing scores define similar individuals for the decision of college admission. To assess people in examining the potential discrimination exists in model predictions, we propose visual analysis of discrimination in machine learning and develop an interactive visualization tool. This tool contains two parts, a discrimination discovery module and a visualization module. In the discovery module, given a model prediction task, a set of resolving attributes that are important for the final decisions are identified to help us define similar individuals. For example, for predicting the income of a person, similar individuals are highly likely to have similar work classes, education level, and working hours. Meanwhile, a series of classification rules are also trained to describe how a decision is made by a machine learning models. If a classification rule changes based on a protected attribute, a potential discrimination item set can be identified. For example, if males and females with the same working class, education level, working hours have different incomes based on their gender, we might suspect there is an unfair treatment. The three-step pipeline reveals a number of potential discriminatory item sets and helps users better understand the discrimination exists in model predictions. However, a discriminatory item set can have a known and complex definition, and those item sets are usually intertwined together. As a result, analyzing those discriminatory item sets can be confusing. An effective visualization is needed to assist users in the analysis. To present the known and complex definition of discriminatory item set, we present attribute matrix. In this design, each row corresponds to one item set, and each column indicates one attribute. The solid part in the rectangle indicates the value of the corresponding attribute. The intertwining relationships result from the fact that one individual may belong to different items at the same time. To better present those relationships, we extend the traditional ordinal diagram and propose ripple sets. In traditional ordinal diagram, a set is represented by a closed shape. It's hard to read when the sets are intertwining with each other. We disentangling the intertwining in item sets and use closed shapes to indicate the maximum inseparable subsets. Meanwhile, to facilitate understanding the subset relationships, subsets belonging to the same set are put together. I will skip the algorithm details here and please refer to our paper for more information. Putting the attribute matrix and the ripple set together, we get the interface of our tool. A scatter plot is also added to provide an overview of those item sets. In the scatter plot, each point stands for an item set. The X position indicates the degree of the discrimination, while the Y position indicates the size of the item set. Users can change the threshold or modify the definition of discrimination. Here, I present a case where users analyze models that predict whether a student will get a high test score. More use cases are provided in the paper and the supplementary material. The user first chooses the model with the highest accuracy and try to understand discrimination in the prediction of this model. Color indicates the direction of discrimination. Orange indicates decisions that favor female students, while green indicates decisions that favor male students. The user first finds that in all discriminatory item sets, the upset day is larger than 7. This observation can be easily explained by the histogram, which indicated that most students who are absent less than 7 days were predicted as a high-score class. The user then examined the discrimination among different item sets. High color saturation indicates severe discrimination. Multiple clusters indicated intersections between item sets. The user can expand the corresponding row for more detailed analysis of the intersections. Therefore, the user can easily identify the item sets with more severe discrimination and its intersection with other item sets. The user then compared this model with random forest, a model with the second highest accuracy. Overall, random forest has more discriminatory item sets than XGBoost. Interestingly, 4 of the 5 discriminatory item sets in XGBoost also existed in random forest. The only difference was in the second item set, where the ripple set of random forest has more hollow items than XGBoost. In other words, XGBoost was more likely to predict students in this item set as a low-score class. Considering that most discriminatory item sets in XGBoost also exist in random forest, and that random forest had more discriminatory item sets, the user concluded that XGBoost was a better choice than random forest, even from the fairness perspective. Many methods have been proposed to remove discrimination in model predictions, but may also reduce the model accuracy. To reduce accuracy loss caused by discrimination removal methods, the users may want to identify and only remove severe discrimination, that is, discrimination with high unfairness scores and discrimination towards critical groups. For example, the user was concerned with the discrimination happened to hardworking students, such as students with no absentees or active discussion. Item sets with high unfairness scores, in this case risk difference scores, can be easily identified through the color. For the critical group, the user first examined the students with no absentees and selected the items whose absent day is less than 7. He didn't open the row since the one circle in report set indicates no complex intersection. The user then checked the students with active class participation by examining the value of raised hands. He expanded the rows and selected an item set that also had a high value of discussion. By providing more detailed information, our tool enables users a precise control of the discrimination removal and reduce the possible accuracy loss. Apart from the use cases, we conduct a user study to assess utility of the proposed visualization. Compared with the baseline, users can complete the analysis tasks more quickly and accurately using our tool. To conclude, in this work, we propose an interactive visual analysis tool and a set of visualization designs to assist the analysis of discrimination in ML model predictions. We provide a user study and use cases to assess utility of the proposed analysis tool. Meanwhile, we recognize some limitations of this study. First, allowing users to define discrimination may introduce subjectivity to the analysis. Second, we only support the analysis of one predicted attribute and doesn't consider the hidden attributes. Also, this study provides limited support in explaining the identified discrimination. It is a promising direction to combine the analysis of discrimination with explainable machine learning techniques in the future. Thanks so much for your listening.